the million-dollar question we're after here is, suppose we feed the large language model with alternative physics. Will it still be able to, in context, learn it and give you good prediction about the future? Okay, so friends, Roman countrymen, my name is Tony Liu. I'm a PhD student from Cornell University. And today I want to tell you guys about how large language models can learn the governing principles of dynamical systems, which reviews a in-context neural scaling law. That's a bit of a mouthful. Let me try to unpack it a little bit. Basically, our main observation is that large language models are, there are prompts here. Our main observation is that large language models are able to learn from in-context time series data and make probabilistic predictions about the next state. I will demonstrate exactly what I mean by this using a noisy logistic map. So for those unfamiliar with the math lingo here, logistic map is a type of 1D chaotic system where the future is really difficult to predict based on the past observations, but there does exist a deterministic relation between future and past. My system is governed by a 1D recursive equation where each state, xt plus 1, is a random variable that depends only on the previous state, xt. The relation is a nonlinear function f. By the way, do I have a timer here? Oh, yes, I do. It's governed by a nonlinear function f with some Gaussian noise injected into it. Condition on the history, the next state is always distributed as a Gaussian distribution, which is here shown in red. Note that the y-axis is the probability density and is shown in log scale. The ground truth in this case is a Gaussian distribution in red. And the prediction from the large language model in this case is llama 2 13b with no fine-tuning and prompt engineering whatsoever, gives you a pretty good prediction shown here in the blue histograms. Now, before flashing more results at you, I want to backtrack a little bit to talk about our methodology. That is, how do I exactly extract the prediction from llama 2, the blue bins you are seeing here? Well, so it's a very simple methodology, mind you. Basically, given a 1D time series that we're interested in predicting, we serialize it in the form of comma delimited multi-digit numbers. In this case, each state is represented as a 3-digit number. And then we just pass this string into a large language model with no fine-tuning at all. And because of the way, it's a little bit messed up, but I think it's still intelligible. Basically, due to the way the large language model is trained, it's going to naturally give you the prediction for the next digit. Notice it's not the next state, just the next digit, which in this case is the 100-digit. You can think of this 100-digit prediction as a very coarse outline of a probabilistic prediction. And then you can ask the large language model to give you the next digit, which basically delves into one of the existing core spins and refines it by dividing it into 10 uniform bins. And we keep doing the same thing until we reach the end of the number. Once you do this sing and dance, you are gonna have on your hands what we call a hierarchy PDF object. It's a probability mass function with a hierarchy of resolutions. And in fact, in our paper, we provide an algorithm that you can use to recursively go into each of the core spins and refine it until you have the desired precision. We call this the hierarchy PDF algorithm. You might think this might be very expensive because you're basically doing a tree search using large language models, but it can be made surprisingly efficient if you cache your K, Q, and V matrices of the transformer in a clever way, which we provide in our repo. So check it out. But once you do this, using this algorithm, you can extract a very high precision probabilistic prediction for the next state of any dynamical systems. And here I'm plotting the prediction at different levels of context length. So naturally, the more context you have, the better you can predict the next state. But it's quite surprising that a large language model can do this. So in this case, llama slowly converges to the ground truth. I should mention that the ground truth is not a static Gaussian function. It drifts because it's a chaotic system. I would also like to draw your attention to the limiting case at no data. So when there is no data, large language model, in this case Llama here, gives you a uniform distribution, which makes Bayesian sense. When I give you no information at all, you should return to me maximum ignorance, which is maximum entropy encoded by the uniform distribution here. And of course, we can quantify this observation using any of your favorite loss functions, like KL divergence, or in our case, the Bhattacharya distance, but it doesn't really matter. You can even use cross entropy if you want. So what I'm showing you here is the loss curve for the in-context learning of the logistic map I showed you earlier as a function of context length plotted in a log-log plot. It shows up as a straight line. At this point, you shouldn't really surprised to see power laws, but still, I find this quite surprising. And in our paper, we actually we repeated some experiments on all sorts of dynamical systems. Some are stochastic, some are not. We even tried randomly generated Markov chains with random transition rules. What I would like to draw your attention to this particular example here called the Lorentz system that shows up as this green curve, broken curve here. So for those unfamiliar with the Lorentz system, it is a three-dimensional chaotic system governed by a set of three ordinary differential equations. But again, this is a language model. Language is a 1D time series. So you have to project the 3D system into a 1D line and then feed into a large language model. Mathematically, it's well known that when you reduce a system in such a manner, you have on your hands a partially observed problem, which is known to still be deterministic. You still know how to, you can in principle predict the future from the past. However, in the applied math community, there's no clear theoretically optimum algorithm you can use to construct such a prediction. This is why I think it's very surprising that large language model is able to do this. And it achieves a very similar scaling law compared to, say, the noisy logistic map. Now, why am I so excited about scaling law here? Well, because many existing learning algorithms have characteristic scaling law. For example, gradient descent or the stochastic variance of it typically have a power law of -1/2. And you can have similar scaling laws for other learning algorithms like gradient descent with momentum if you turn off the but you have to measure them using a good loss function, but that's the only caveat here. I therefore speculate that the existence of these consistent scaling laws could be a telling signature of a consistent learning algorithm that the large language model is implementing implicitly during the forward inference process. Characterizing this in-context learning algorithm is, in my opinion, a very exciting, if also very challenging direction of future research. Well, because there's no a priori reason why we should believe that our large language model is solving these problems using a human algorithm, or even an algorithm that's intelligible by human experts. Fortunately, ever since the publication of our paper on arXiv, we have inspired several labs to look into this direction. So here I just want to make a few shout outs. Zachary and colleague derived the theoretically optimum learning rate for learning Markov chains. And they were able to show that the newest large language model, such as Gemma 2, is able to closely saturate the theoretically optimum lower bound. This suggests that Gemma is probably using the theoretically optimum in-context learning algorithm to learn these dynamical time series. And Katamnani et al. Investigate the numerical method implemented by transformers to solve ODE systems. And they were able to show that the way a pre-trained transformer solves the ODE system is very similar to what the applied mathematicians call the matrix exponential method. So this is a very fortunate case where the large language model does think similarly to human experts. And lastly, yours truly and his colleagues have a follow-up work that shows large language models can perform density estimation Density estimation is a cornerstone problem in classical statistics, where you observe a discrete collection of data points, and from the empirical observation, you try to reconstruct what is the underlying probability density function that the data are sampled from. This is very simple problems, but it does underpin almost all probabilistic modeling problems that you care about in modern machine learning. We were able to show that the way Llama 2 solves density estimation is closely related to the kernel method. So if you're an old timer from the 80s and you really like kernels, make sure to check our paper out. So with that, I would like to thank you for your time, and I'll take some questions.
Yeah, thank you.
Hi, so I'm kind of one of those old timers. So back in the days when I want to say neural ODEs used to be the method for doing these kind of predictions. And so just want to hear your thoughts about, like is there room for intersection of neural ODEs with these transformer types, or really these LLMs are becoming more the preferred method over neural ODEs?
This is a good point. So neural ODE, okay, I'm not crazily familiar with ODE's neural ODE literature, but my impression is that you can think of transformers as a type of neural ODE if you take the limit of infinitely deep transformer, then each layer is roughly implementing DT, right? I think I know of a work which I can tell you offline, that if you train a transformer for long enough, then each layer is roughly implementing that. You are not explicitly asking a transformer to solve the problem in the ODE way, but the transformer does converge to it. So it is quite surprising that a transformer is able to discover like a humanly preferable way of solving ODE system, even though you are not asking it to. As to whether transformers are going to be more performant than classical ODE, I doubt it, because transformers are not designed to be transparent or interpretable. And when it comes to ODE, we really care about what exactly are the coefficients we're learning from the system. So I think pins are still going to be your go-to method for a while. Yeah, thank you.
Thanks for the great talk and really interesting work. I'm curious, especially because a transformer or a language model probably didn't see that kind of data during pre-training.
Probably not, yes.
Have you tried that with or with randomly initialized large language models? Do you get the same performance, or
like ablation study?
Or just
right.
Do you even need a trained llama or gemma to get the same scaling law for
I
that
do
kind
think,
of data?
right. So I haven't done that, but I do think you need a well-trained large language model, because you can train a small model to do this kind of problems, and you don't always see scaling laws. And small models oftentimes do not even converge. Like if you train it on a certain type of chaotic system, it does not generalize to other chaotic system. So this generalization is quite non-trivial, and I doubt a randomly initialized large model can do this.
Very interesting.
Thank you.
One quick question.
Sure. Why can LLMs do this? They're trained on text data, and you're taking the 10 digits, which is a very, very tiny subset of the tokens.
Right. I ask myself that all the time. My guess is that there must be some sort of a numerical data somewhere on the internet, right? And if the large language model has seen enough, I don't know. Sorry. I think I had an answer at the beginning of the sentence, but I don't. Right. Let's talk offline.
Yeah.
Yeah.
Appreciate that. All right, let's thank our speaker again.